So the tree diagram looks very, very complicated and scary with all this probability notation, but I'm going to impress upon you the need to not get bogged down with the notation as it's written right here, but to understand the meaning of what's on these branches. And I think through the use of several examples in this section, we'll see how to build these trees neatly and well organized and fairly simply. So several examples today. Here we go. So we have an archery student, an archery member. Probability that he hits the bullseye is 0.8. Samuel takes 2 shots. The shots are independent from each other. We're going to represent this information on a tree diagram. So this first set of branches represents shot 1, and he either hits on shot 1 or he misses on shot 1. And what's the probability of these things? Well, the probability that he hits is 0.8, and the probability that he misses is 0.2. And then there's event 2, and event 2 can happen as a result of either one of these. So after he hits, he could hit or miss, and after he misses the first shot, he could either hit or miss the second shot. And what are the probabilities that go on here? Well, they're independent, so the probability that he hits again is still 0.8. The probability that he misses is still 0.2, and 0.8, and 0.2. The probabilities don't change from one event to the next because they are independent. So what's the probability that he hits 2 bullseyes? Well, let's look at the path that we would take for that. That path is the only way that he could get 2 bullseyes. So probability of 2 bullseyes, in other words, probability of a hit and a hit, well, that is going to be 0.8 times 0.8, better known to us as 0.64. Hits only 1 bullseye. Well, to hit 1 bullseye, that can happen 2 different ways. And let's identify what those 2 ways are. We could hit first and then miss, or we could miss and then hit. So probability of hit and miss, or probability of miss and hit. So the pink branch across the top, we're going to have 0.8 times 0.2, plus we add the 2 different branches, 0.2 times 0.8. We have 0.16 plus 0.16, or 0.32, as our probability. Okay, so now what's the probability that he hits only 1 bullseye? Okay, only 1 bullseye. Sorry, at least 1 bullseye. So that would mean 1 or 2. So there's 2 ways that we could do this. We could add these together, because that would be hit and miss, or miss and hit, or hit and hit. Or we could take this as 1 minus the probability of no hits, which would be 1 minus 0.2 times 0.2, which is 0.96, and that's what you get if you add these 2 together. But anytime you see at least 1, again, I've said this before, but always treat that, it's always going to be easier to do 1 minus the probability of none than it is to add together all the different possibilities that you could have. Example 2, 3 white, 7 black balls in a box. 1 ball is taken out, the color is noted, and then it is left outside the box. And then another ball is taken. So this probability situation, the events are not independent of each other. So we're going to take a ball out, and that ball is either going to be white or black. And then when we take a second ball out, again, the possible things that could happen is it could be white or it could be black. White, black. And we need to assign probabilities on these branches. So on the first pick, what's the probability of getting a white ball to take out? It's 3 out of 10. And a black one is 7 out of 10. But now remember, for the second part, we have taken a ball out. Now there's not 10 balls in the box anymore. Now there's only 9. And so this is on the original probability tree diagram. This is where it says the probability of A given B. So we know that a white one was taken out. That means that there are 9 balls total and only 2 of them are white, but 7 of the 9 are black. Down on the bottom part of the tree, we took a black one out, so there's only 9 balls left. 7 of them are white because we took the black one, and 3 of them are white, and 6 of them are black. And now that we have this tree diagram organized, we can answer these questions. Probability that they're both white. Probability of white and white. Okay, so that would be across this top branch. So we're doing 3/10 times 2/9. Or 6 out of 90, we can reduce 2 over 30, which is 1 over 15. Both are black. Okay, that's going to be across the very bottom of the tree. Probability, black, and then black. So 7/10 times 6/9. 6/9 reduces to 2/3. 14 over 30, also known as 7/15. You'll find that once you're able to get this tree built with the probabilities labeled on it clearly, these probability questions are actually quite manageable to get through. And you know what? We can take this multiplicative property law. Normally we just have probability of A and B is equal to the probability of A times the probability of B given that A occurred, but we can extend it to a third event or even more. So A and B and C, well, we tack on the probability of C given that A and B has already occurred, and this is easiest to see again on one of these tree diagrams. Okay, so this example, we have 12 toys, and there are 7 cars, 5 trucks. A child can take 3 toys off the shelf. Now, I can relate to this question. My young son loves his toys. He loves to take them off. Doesn't always like to put them back, but he likes to take them off. And he's only going to take 3. So I want to create a tree diagram to represent this information as to what can happen. So the first event is he either chooses a car or he doesn't. And it would look like this. Choosing a car is 7 out of 12. Not choosing a car is 5 out of 12. The next event is either choosing a car or not choosing a car. And the probabilities here are, well, now he took a car off, remember, going across the top. So now there's only 6 cars out of 11 total. There's still 5 trucks, 5 not cars, out of the 11. Across the bottom, he's taken a truck, so there are still 7 cars out of the 11, but now there's only 4 not cars out of the 11. The third event will have another pair of branches coming off each one of these, and now we have to label the probabilities here yet again. So again, we took car and then car, so now we're down to 4 cars out of 10. We took car and then car, so out of 10 there's 6. Notice every pair of branches, it'll always add up to a probability of 1. It's helpful for filling out this tree. So now he took one of each going down this path. So there are, okay, so after he takes a car, there's 6 cars. There's still 6. 6 out of 10. He took 1 car, 1 truck, so now he's down to 4 trucks out of 10. Across the bottom, a car and a truck got taken. A truck and a car right here. Truck, car. So now he has 6 cars out of 10. And 4 trucks out of 10. Across the bottom, he's taken 2 trucks. So no cars have been taken. So 7 out of 10. But 2 cars, so now he's down to 3 out of 10 trucks left to pick. Wow, there we go. That's the most complicated thing of this problem, is getting this ridiculously big tree drawn. Once you have it, these calculations are pretty straightforward, I think. Find the probability that all the toys are cars. Okay, we follow the branches that are car, car, car. So 7/12 times 6/11 times 4/10. Multiplying these together, we get 7 out of 44 once we reduce. Part 2, the child picks at least one car. There's that phrase again, at least one. What do we do? How do we deal with that? Remember, it's 1 minus the probability of none. So 1 minus the probability of no cars is equal to the probability of at least one. So the probability, this would get messy if I tried to count all the different probabilities where I'm getting at least one car in it. It's going to be every path except for one of them. So what's the path that has no cars on it? That's this very bottom one. So 5/12 times 4/11 times 3/10. And that's 1 minus 1/22. So this probability that I get at least one car is 21 out of 22. You know, my 14-month asked me this question last night. He said, "Dad, what's the probability that I pick at least one car when I do this? I'm really concerned." And so we figured it out, and he came up with the same result. So I hope that all of you can do that too. Just kidding, we didn't really. So last example, we've got Toby. He's a tennis star. He's awesome. He found that when he gets his first serve inbounds, the probability that he wins is 0.75. When he uses his second serve, that is, when he misses his first one, there's a 40.45 chance of him winning the point. He's successful in getting his first serve in on 3 of 5 occasions, and his second serve in on 3 out of 4 occasions. So we need to make a tree diagram for this scenario. When Tony serves, it's either in or out on his first serve. So this first branch is for his first serve. And it's in 3 out of 5 times, which means it's out by default 2 out of 5 times. And when it's in, we want to look at whether or not he wins the point. He either wins or he loses. And it says that when it's in on his first serve, he wins 0.75, 75% of the time, which means he loses 25% of the time. If the first serve goes out, he gets to serve again. He gets one more try, and that serve will either be in or out. And it says the probability that his second serve is in will be 3 out of 4 times, 3/4, which means the probability that it's out will be 1 out of 4. So if it's in, what's the probability that he wins? Well, it's 0.45. And losing would be 0.55. So he's going to hope that it's in on his first. Okay, so we have this tree diagram made. We want to find some probabilities now. Find the probability that the next time it is Toby's turn to serve, he wins the point. So this is a combination of two things. That's a combination of that branch and that branch, because on both of those branches he wins. So this probability will be 3/5 times 0.75 plus 2/5 times 3/4 times 0.45, which is equal to 0.585. For part B, this is A, B, given that Toby wins the point, what is the probability his first serve was in? So this is now conditional probability. So what's the probability that first is in, given that he won? I'll remember the formula for this. It's the probability of first in, intersect, win, divided by the probability that he wins. Well, we know the probability that he wins. That's 0.585. And now what's the probability that the first serve is in and he wins the first point? First serve is in and he wins the first point. That is this top branch. So this is going to be 3/5 times 0.75. You have to be able to translate from this notation that we see in our formula and the context of the problem. So this means first serve is in and he wins the first point. Top branch of this. This probability is 0.769 given to 3 significant figures. So I hope that you're seeing that the probability calculations themselves are not difficult if you have your tree drawn. The tree can be the confusing part, especially when you're looking at probabilities that are not independent of each other. But we are finished with today. If you have further questions with setting up these trees, the best thing to do is see how trees are made by other people.